Welcome to this explainer where we're going to embark on a journey straight into the invisible world. We're going to see how manipulating matter at the absolute atomic level is actively revolutionizing our reality. To put things into perspective right away, your fingernails grow about 1 nanometer every single second. Crazy, right? We hear the word nano thrown around all the time in tech and science, but today we're going to unpack exactly what that means. We're looking at the fundamental building blocks of our universe and seeing how scientists aren't just observing them anymore, they're completely rearranging them to build our future. All right, let's take a quick look at our flight plan, which breaks down this massive topic. We'll start with the basics of the nanoscale, check out the specialized tools we use, how we actually manufacture at this tiny size, real-world applications, the future of nanoelectronics, and finally, the hurdles we still need to overcome. So let's dive into Section 1, Welcome to the Nanoscale, and the bizarre rules of the atomic world. Just to ground us before we get too deep, here's the technical definition of nanoscience. The absolutely crucial word to focus on here is interdisciplinary. This isn't just chemistry and it's not just physics. It's the ultimate crossover. It requires an integrated knowledge of physics, chemistry, biology, and engineering to actually manipulate those fundamental building blocks at the atomic level. It's a highly collaborative, cutting-edge frontier. Now, when we say nanoscale, we are operating strictly within the realm of 1 to 100 nanometers. To put that into perspective for you, a single sheet of standard paper is about 100,000 nanometers thick. So yeah, we are talking unbelievably small. At this specific ultra-tiny scale, materials suddenly develop an incredibly high surface area to volume ratio. That means way more of the material is exposed to the outside world, which completely changes how it interacts with its environment. Plus, the standard laws of physics kind of take a back seat, and intense quantum effects take over, leading to some totally novel phenomena. A really perfect example of this paradigm shift is gold. Bulk gold is that shiny yellow stuff you might wear on your finger, and it's relatively unreactive. But if you shrink that exact same element down to the nanoscale, quantum effects literally make the gold particles appear red or purple. It's wild. It's the exact same fundamental material, but simply changing its physical size completely alters its optical properties and makes it highly reactive. To make sense of this invisible world, it really helps if we logically organize these building blocks by their dimensions. We start at zero-dimensional structures, like nanoparticles and quantum dots, which are essentially tiny little spheres. Then we stretch them out into one-dimensional structures with high aspect ratios. This means they're incredibly long and thin, almost like a microscopic noodle. We're talking nanowires and carbon nanotubes, which happen to have exceptional mechanical and thermal properties. Finally, we build up to two-dimensional structures, which are nanoscale in thickness, but stretch out flat like a sheet of paper, with graphene being probably the most famous example of that. Moving right along to Section 2, Seeing the Invisible. Let's look at the specialized tools we need to look at atoms. What's truly interesting here is how we cut through all these dense scientific acronyms to figure out exactly which tool we need for the job. Standard light microscopes simply cannot resolve things this small. No way. So, if we want high-resolution topographical imaging down to just a few nanometers, we bounce a focused electron beam right off the surface using SEM. If we want true atomic scale analysis, we shoot high-energy electrons completely through a thin sample using TEM. And if we literally want to feel the mechanical properties of a surface, we drag a sharp microscopic probe across it using atomic force microscopy. It's honestly like reading Braille, but at the atomic level. All right, Section 3, How we make tiny stuff. Let's get into fabrication at the atomic level. Nanofabrication relies heavily on a dueling methodology. On one side, we have the top-down approach. This is exactly like sculpting a statue. You start with a big, large block of material and precisely carve or etch it away until you're left with nanoscale features. On the other side, we have the bottom-up approach. This is a lot more like building with Legos. You encourage the controlled growth or self-assembly of structures, literally putting them together atom by atom or molecule by molecule. So the crucial takeaway is how a top-down method like photolithography actually works in reality. Because fun fact, this is exactly how our modern computer chips are made. First, you coat a substrate with a light-sensitive material called photoresist. Second, you shine light through a template to transfer incredibly complex, tiny patterns onto that substrate. And finally, you etch away the exposed material to leave behind precise nanostructures. You're systematically carving away using nothing but light. Conversely, in bottom-up fabrication, we have incredible mind-bending techniques like DNA origami. This is an absolute masterclass in exploiting the rules of nature, because scientists now understand how the biological code of DNA naturally wants to pair up and fold. They can literally program these molecules to naturally organize and assemble themselves into exact predetermined 2D and 3D shapes. And the best part, we do it without having to physically carve a single thing. Let's jump into Section 4, Nanotech in Action. This is how the science is actively transforming our physical world. The real-world utility we're seeing here is truly staggering. In medicine, nanoparticle-based therapies can selectively target tumor cells, delivering potent drugs directly to the cancer, while entirely sparing the surrounding healthy tissue. In energy, quantum dots are being used right now in solar cells to harness a much wider range of the solar spectrum, massively boosting their efficiency. For environmental monitoring, we use graphene sensors that are so sensitive they can detect a single solitary molecule of hazardous gas. And nanostructured membranes are completely revolutionizing water desalination by super efficiently filtering out salt ions and contaminants. Which brings us to Section 5, the future of nanoelectronics, where we are desperately pushing past the limits of silicon. For decades now, the tech industry has been governed by Moore's law. This is a principle stating that the number of transistors on a microchip roughly doubles every 2 years. This is the exact reason why our computers and phones have rapidly become exponentially faster, smaller, and more energy efficient over our lifetimes. But here's the catch. Traditional silicon-based transistors are currently hitting a serious physical wall. We are making them so tiny that they simply cannot function reliably using standard silicon physics anymore. So, I really want you to ask yourself, how do we keep innovating and making our tech faster when we literally run out of physical room on a silicon chip? What happens when we just can't etch any smaller using top-down lithography? Well, nanoelectronics steps in with some miraculous replacements. Instead of silicon, we can swap in carbon nanotubes, which offer absolutely exceptional electrical and thermal properties. We can use graphene, which has such high carrier mobility that electrons can zip through it with almost zero resistance, which is absolutely perfect for flexible, transparent electronics. We can build single electron transistors that operate by controlling the flow of individual electrons, meaning they consume almost no power. And then there's spintronics, which is just mind-blowing. It utilizes not just the charge of an electron, but its actual physical spin for information processing and data storage in things like magnetic random access memory. Finally, we reach Section 6, Challenges and Future Horizons. Let's look at the actual hurdles ahead for nanomanufacturing. What you really need to take away from this explainer is that building at the nanoscale isn't just expensive, it is deeply, deeply complex. Scalability is a massive roadblock. I mean, getting DNA to fold nicely in a sterile lab is one thing. Mass-producing billions of perfectly identical nanodevices is a whole other beast. Environmentally, because these structures are so tiny, slight changes in temperature, humidity, or even a microscopic speck of contamination can completely destroy their performance. And crucially, we have to talk about toxicity. The very thing that makes nanomaterials amazing, their high reactivity and ability to easily cross biological barriers, also means they can interact with living systems in unpredictable ways. This raises huge, important questions about safe disposal and human health. But despite those massive challenges, the trajectory points toward incredibly rapid advancement. We are looking at a near future with nanorobots capable of swimming through your bloodstream for minimally invasive surgeries and real-time internal monitoring. To beat the death of Moore's law, we're aggressively moving toward 3D integration, vertically stacking nanoscale components to increase device density. We're setting the stage for highly scalable quantum computing platforms using nanoscale superconducting qubits. And to finally solve that manufacturing bottleneck, high-throughput methods like roll-to-roll processing are being optimized as we speak. The potential here is frankly limitless, but it definitely demands responsibility. So I'm going to leave you with this final provocative thought to ponder. As we master the incredible God-like power to manipulate matter atom by atom, how do we guarantee this invisible revolution remains safe for our bodies, our privacy, and our environment? Thanks so much for exploring the invisible world with me today. Stay curious and keep questioning the fundamental building blocks of our reality.